And of course, whenever there's any decision about, oh, we want to develop something back here, we want to put in aquaculture, or we want to do any kind of coastal development, more and more we're seeing public participation forums. And of course, not everybody can look at a planimetric map and understand it and get it. There's a large percent of the population that their brain doesn't see maps and interpret them correctly. So to be able to visualize the terrain in 3D and so forth is not only fun for us as professionals, but also quite useful for people to immediately understand what is going on in that estuary in terms of the lows and the highs and where maybe sediment has infilled something. Now we can become more quantitative and actually use the input data here for a hydrodynamic model to look at how fast are the currents moving. And you'll notice the currents are, fairly slow, fairly stagnant back here. So in terms of flushing and maybe food supply, probably not a good place to site aquaculture back here, compared to perhaps some of these other areas where we see more flushing and more movement of the water. This is Mike 21 depth average model. Now, of course, people are also interested in, well, what if we have a spill, whether it be oil or excess food for an aquaculture operation, or feces, or runoff from bacteria. We need the hydrodynamic model in order to then start moving those particles and see where they end up, whether they get flushed out of the system or whether they're trapped, how quickly do they come ashore. And of course, for all these particles, we can have different densities and buoyancies and decay rates and so forth. This is really just an illustrative example to show the effect of having this detailed bathymetry data does nothing but help the model in terms of predicting its accuracy. Okay, let's talk a little more about this idea of the exponential decay of light with depth, so the attenuation, essentially. And here we have the original LIDAR intensity, we have the depth. So what we can do is go through and essentially sample the same land cover, sand in this case, all along this at deeper depths to essentially build this curve up. Because let's face it, in reality, nothing ever looks this good like it does in the textbook. And that's essentially what we're doing here to depth normalize our intensity. So there's the original intensity. So remember, dark could be eelgrass or it could be deep. We then go through and do the depth normalization where we're bringing up those low intensity values because they're deep rather than being dark because of something on the bottom. So now we can more readily differentiate the eelgrass patches from the channels, for example. And of course, the same principle happens with passive remote sensing, with the aerial photo. So we could take the same, because we have the bathymetry now, we can apply that same technique to the air photo. And where we couldn't really see what was going on in this deeper water, it looks like it's mostly sand, according to this process, with some patches of eelgrass at these shallower spots. And then we can do this was a fairly quick and dirty eelgrass. We're doing a little project with DFO right now to map the eelgrass here in a more sophisticated way. This was just a quick method to look to see how well did that help us pull out the eelgrass. As Vlad talked about, and with most remote sensing, we always want to go out and do some ground truth so we understand what is on the bottom. And with LIDAR, since it's an elevation measuring type system, we're always interested as well as how high is that vegetation on the bottom. And with eelgrass, it's typically quite short, so to get eelgrass thickness, ooh, that's a challenge right now. I don't think we're quite there for the thickness component. But in Topo-bathymetric, we were tasked to map eelgrass, and if you go to our website, agr.cogs.ns.ca, you can actually look at these data sets in 3D through an ARC engine viewer there. So let's look in Topo-bathymetric up in the north. There's the bathymetry. Here we've got the intensity merged in. And we've gone through and produced a map that shows sort of range of probabilities, similar to what Jennifer talked about with some of the initial mapping stages there, higher probabilities of eelgrass in those darker greens. And then we looked at ground truth, and this ground truthing I think will, oh, I'm sorry, I don't have the credits here, but this ground truthing data was collected by a scientist at DFO, Mark, as well as Mark from Stantec, and our boat was out here collecting ground truth as well. So we put all those together, and essentially the blue circles are where the eelgrass is present, the triangles are where it's absent, and where we have a yellow circle, it agrees with our map. So we're at about an 80% agreement in terms of mapping the eelgrass at this stage. And this was really our first attempt at mapping eelgrass using the LIDAR, and we've refined things a little bit, and we're continuing to. We've done a similar eelgrass map for Cocan, but now I want to take you to the present. So we were hoping to fly a little earlier in the year. November in Canada is not a great time to fly LIDAR. But Leading Edge now has their own aircraft, and we just got it certified recently to be able to hold our sensor and fly. So these stars represent the areas that we plan to fly, and we're probably 3/4 of the way through that mission, and we hope to be flying on the weekend to finish things off till mid next week. I just want to show you a little bit down here in a place called Shag Harbor in southern Nova Scotia. This is a WorldView 2 image, and this is the ground truthing we've done. They harvest rockweed here that grows in the intertidal. It's this light green band. And what we're interested in with this insert project with Acadian sea plants is, are we able to try to estimate the biomass of that rockweed? So we flew it twice, once at low tide and again at high tide. Here is the low tide bathymetry. We do have one little sliver here. These pilots, they're good, but they're not as good as the guys from Dynamic Aviation who we had last year. There's LEG's new aircraft, but we have good, it's cut off here, the depth, but we're down to about a 9.5 meter depth penetration here down in Shag Harbor, and this is across this profile here. And we can see the channel quite clearly and complete coverage of the bottom. The waters are nice and clear down that area. So here's some of the ground truth that we did to support that. You know, we were concerned if we just flew it at high tide, it'd be like dense shrubs with Topo LIDAR. You're probably not going to get to the ground. So in this case, we were concerned we might not be able to get to the actual seabed, and therefore, how would we really know how high those plants were? So we went out and did quite a bit of work looking at measuring the rockweed, weighing it, looking at relationships between height and the diameter of the clump and so forth. And then flew it at low tide, so we could get the topography essentially, and then flew it again at high tide when all that rockweed is floating, essentially a forest under the water there. And you know, we do some video drops as well. Here was our solution to get really good GPS points in the water. Believe me, he wouldn't have taken a point until it was plumb. But here's how far that pole can extend. We had a couple of our light sensors that we had such a low tide last week that we were looking for them, and oh, there they are on the sandbar. So we took a GPS point. So this thing extends to about almost 5 meters high. Quite something to wrestle with. And we're just shooting some underwater video here. Those are 20 centimeter increments on that quadrat in terms of the height. We dropped it down over one individual piece of rockweed, and you can see the height there. It's a little over about 90 centimeters. What we don't know exactly is how big is that rock there at that particular case. So some very preliminary results. We flew the LIDAR mission on October 27th, then the next day, the high tide mission. And if we look here in detail, we can see this upper band. He's got this labeled as rockweed, being the red is the low tide. I think this is really the rockweed here, this cloud of points in the green. I'm very happy about that. I'm quite excited about that because this shows us we have a real good opportunity to estimate how much volume of material is there, and that's real important to the harvester in order to do a sustainable harvest and be able to predict how much volume of material they can actually bring in from different areas. We also did, we've got 3 areas here with, well, we're not doing Miramichi, these 3 areas here with Mark at DFO, and this shows the coverage at Saint-Simon. We did not, the channel, we didn't penetrate to the deepest part of the channel. But for the most part, one of the end products we'll eventually look for is eelgrass, and we don't expect a lot of eelgrass in the channel itself. So we think with the data we did collect, we're probably in pretty good shape as far as processing some additional products down the road. Very challenging area to map in terms of exposure and the type of fine sediment. Okay. Bay of Fundy. As soon as you speak of the Bay of Fundy, most people say, oh, well, bathy LIDAR will never work there. And probably from here up, I would agree. But the water clarity actually improves dramatically as you move downstream. These are some flights going from the bay up over the North Mountain. And we got 4 meters, in some cases 5 meters. This Rainbow Resources was down off of Yarmouth, 5 meter penetration there. And we did a quick recon flight over Grand Manan because really we didn't know what the water clarity was going to be. And there we've got 10 meters of depth before it's either too deep or too turbid. We haven't processed the photos enough to really make that assessment, but fairly encouraging. And this is obviously a complex area where there's a lot of rockweed there as well. So, to wrap up, the ability of this sensor to penetrate both the vegetation canopy on the land and the water column makes it ideal for a variety of earth science applications and coastal resource assessment applications, which I guess is really what we've been concentrating on. I don't have anything in here about storm surge, but certainly the idea of using those hydrodynamic models to drive storm surge, I think now it actually gives us a chance to model wave run-up in terms of having that near-shore bathymetry that's often been absent. The LIDAR and the ortho photos really have make a nice suite, but turbidity management has to be used, and we have to always be aware of that when you're planning a survey. If you're going to do this, if you're commissioning a survey, then you should think about that and either put that on the responsibility of the vendor or to another agency or yourselves if you have the capacity to do that. Obviously, these continuous elevation models are extremely useful for doing hydrodynamic simulations where we want to know current speeds and flushing rates for things like aquaculture. If there's a spill of some type, where is that going to move in the near shore? And this is where often the data is absent or quite dated. LIDAR reflectance and the topo roughness. The roughness actually gives us a good idea of if there's something vegetation on the seabed compared to being just sand. The roughness tells us some information as well. This has the potential to map seabed cover and obviously repeat surveys. I was really glad Jennifer talked about repeat surveys, and it was mentioned in a few other talks as well. I hope members of the audience don't leave thinking, oh, we've already flown coastal LIDAR here. Good, got it, don't need it anymore. For one, there's many different sensors, different strengths, different weaknesses, so all LIDAR is not created equal. And two, in the coastal zone, there's a lot of value to repeat surveys, as has been demonstrated by other speakers. Depth normalization, I think it's got a lot of potential to go further with what we can see on the seabed itself. So we flew 9 areas in 2014. Things went quite well, and we've got 15 on our slate right now, of which I think we're through about 11 of them. Thanks for your attention.